This is 2.1, definition of the derivative. In this section, we're going to talk about derivative using a formal definition and why we are able to call the derivative the slope of a tangent line. So in this section, we're going to look at a slope of a tangent line in a general sense. So not a slope at a specific point, but a slope at any point. So what I'm going to do is I'm going to take this blue curve here, and this is a quadratic, and I'm going to pick a point on the quadratic and call it x. So right there is x. That means the y value, if I go up and over, is the y value f of x. And so you can see it's labeled x comma f of x. So that's a specific point on the quadratic, but we can change that point. So it is a movable point. Then what I'm going to do is I'm going to pick a second point on that quadratic, because the easiest way to find a slope is to use 2 points. That way you can do rise over run to find that second point. So I'm going to go a distance, and I'm going to call it delta x. So this right here is delta x. And sometimes what you'll see when you're dealing with the definition of the derivative is instead of using delta x, someone will use h to represent that change in x. So delta x because delta means change, but h because it's a little more simplified than trying to use delta x as a variable. So delta x is going to be this distance here along the x-axis. So that means that takes us to a second spot on the x-axis. And that second spot is what's called x plus delta x, or x plus h, because, and let me actually call it h, because I prefer h, because what we're doing is we're starting with the x that we had over here on the left. We're adding a distance to it, so that distance is h. So right here. And so then we have the same x plus that distance h. So if that's the x value, so imagine that we're doing like 2 plus 7. Okay, so we started at 2, we added 7, now we're at 9. And that point that's now at 9, or at x plus h, because we're keeping this generic, has a y value of f of x plus h. And what we're going to do is we're going to take those 2 points that we have and we're going to connect them with a straight line. So this red line right here is the straight line connecting those 2 points, and that's called a secant line. And this isn't secant like you learned in trigonometry, like secant of a function or of a value. Secant is like a geometric term that just means connected by 2 points. Okay. So then what's going to happen through this definition is we're going to take this second point, so the one at x plus h, excuse me, and we're going to slide it closer to our point at x. So we're going to take this second point and we're going to slide it along this blue curve until we get closer and closer to x. And so what's happening when we do that, as we slide that second point closer and closer and closer, is h is headed towards 0. The distance between the 2 points is headed towards 0. And ultimately what we want is we want h to equal 0. We want the second point to be the first point. The problem with that is we can't find a rise over run if we only have 1 point. And so we introduce this idea called a limit. And that's the notation that you see up here at the top. So this limit, as h approaches 0, is another way of saying point number 2 gets closer to point number 1. Okay, and that's just a calculus way of saying, let's move something. We had 2 fixed points, now let's take that second point and move it. Well, the slope of that secant line, if I do rise over run, or if I do our slope, m equals y2 minus y1 over x2 minus x1. Hopefully that looks familiar from Algebra 1. If I incorporate the points that we have, and I'm going to highlight them in green, so this point and this point are the 2 points that we're using, I'm going to end up doing f of x plus h minus f of x over x plus h minus x. Well, in that statement, the x's are going to cancel in the bottom. So I'm going to be left with f of x plus h minus f of x over h. And that is this statement right here up at the top. So that statement is your rise over run, or your slope of the secant line. Okay. So it's difficult to show this in a static image. So let me go over to Desmos and show you what this looks like if we actually try it with a moving image. So here's the same picture that we were looking at. We have our point at f of x delta x, or I'm sorry, at x f of x, and at x plus h f of x plus h. So we have our 2 points. Now what's going to happen is I'm going to take this second point at x plus h, and I'm going to slide it closer to the other point. So what you can see is that red line is becoming closer and closer to the blue line until that red line is basically a tangent line. It's just skimming the line. Okay, so ultimately what we want is we want the 2 gray dots to go on top of each other. Unfortunately, in this model, it just makes my tangent line disappear. So we'll get really close to it and see that that red line is almost, and for all intents and purposes, is a tangent line. Okay. So what we've shown here is that by taking the limit of f of x plus h minus f of x over h, that we have found the slope at a single point on that blue curve, as opposed to a slope at 2 points on that curve. Okay, so that introduces us to the definition of the derivative. Let's talk a little bit about some of the notation that you're going to see. So the notation on the left here, f prime of x, is the one that you're used to seeing from the last unit. So this is f prime of x. Okay, and all of these are the first derivative at x. And this notation was invented by Sir Isaac Newton. So this is Isaac Newton, who approached this from a functional notation perspective. The second notation, we usually say when we read it, dy over dx, or the derivative of y with respect to x. And this was developed by Gottfried Leibniz, who is the unspoken father of calculus. Isaac Newton is generally recognized as the father of calculus, but Leibniz was the other one. And he approached this from a local linearity perspective, where Isaac Newton approached this from a different perspective. Okay, so a lot of times when you see the function y, you'll either see dy dx as its derivative, or you'll see y prime. So usually dy dx and y prime are kind of interchangeable. Then what you'll see is you'll see the expression version of a derivative. And this is what you guys were seeing in your I Notice, I Wonders last week. And a lot of people were wondering what the D stood for. So d dx, written in front of here, says the derivative with respect to x. And this is our way of taking the derivative of an expression. All of the other notations are function notations. So this is for a function, and this is a function, and this is a function. But this is an expression. Let me write this sideways. Okay, and this is an expression because it's kind of like a square root. It's saying take the derivative of what follows, as opposed to here's a function, now take the derivative. So same idea. The last notation here is this is actually a very outdated version. So this is outdated notation. But you will see this in older textbooks, and it says the exact same thing. It says take the derivative of y. So it is an expression notation. Okay, so you'll see all of those notations, but they all basically mean the same thing. Take the derivative. So then what we're going to do next, now that we've talked about notation, is actually apply that definition of the derivative. So what you'll see in directions is you'll see find the derivative using the limit process or using the formal definition. You'll see either notation or either wording to tell you that you're using definition of the derivative. So our function is called y. So that means we're going to be finding y prime of x. The definition of the derivative says take the limit as h approaches 0 of your function y of x plus h minus your function y of x divided by h. So that's just copying over the definition. Then what we're going to do is we're going to come up with what is y and what is y of x. So over here, I'm going to write down y of x plus h and y of x. Well, y of x is usually pretty simple because y of x is defined for us. We're told y of x is x. Y of x plus h says take your x and replace it with x plus h. So this right here, you're going to replace x. So we had x, just plain old x in this function. If we replace the x with x plus h, we get x plus h. It's very important to note here, I am not taking the original function and just adding h to it. I am replacing the x. So another way of thinking of this is I've replaced it, so I put parentheses around it. So then I'm going to go over here to my limit definition, and I'm going to say the limit as h approaches 0, and I'm going to put in my y of x plus h, which is x plus h. I'm going to subtract my y of x, which is x, and I'm going to divide by h. So then in the top, I see x minus x. So I'm going to go ahead and cross those out, which leaves me with h over h. And so then h over h is 1. And a limit, when you evaluate this, so now we're going to evaluate a limit. Important thing to remember is a limit is a y value near, whoops, h approaches 0. So if I'm dealing with the y value of 1, okay, so limit is a y value. If I'm dealing with the y value of 1 as h approaches 0, that means that at 0, the y value is 1. So it's almost like I'm saying plug in 0. So let me write that here. Another way of saying this is plug in 0. Well, if I plug in 0, there's nowhere to plug it in, which means I'm just going to get 1. So y prime of x equals 1. So if we think back to what we talked about in the first unit, whoops, I've got to get rid of that. There we go. So if we think about the first unit and we deal with the original function here, so the original function is y equals x, looks like this. Derivative is slope, so remember slope gives us derivative. The slope of this line is 1, so the derivative must be 1. And that's what we got when we did the definition. So this one is a little interesting to deal with because it is just a linear function. Let's try our process with a quadratic function. So to find f prime of x, I'm going to go ahead and I'm going to say this is the limit as h approaches 0 of f of x plus h minus f of x all over h. So it's just copying that definition of the derivative over again. Then I need to identify f of x plus h and f of x. F of x is always the easiest because that's just the function that was defined for you, so just x squared. F of x plus h means take your function and replace the x. So I'm going to take the x out. So it was x squared. I'm taking the x out and I'm leaving parentheses. And in those parentheses, I'm putting x plus h. When I have stuff that's squared and cubed, what I like to do in this process, it's going to make my life a little easier, is I'm going to go ahead and expand this. So this is x plus h times x plus h. If I FOIL this, or I do the box, or whatever you learn to expand quadratics, I'm going to get x squared plus 2xh plus h squared. Okay, and we can talk more in class about which method you prefer. So then I'm going to set up my derivative. So f prime of x is going to equal the limit as h approaches 0. I'm going to put in my f of x plus h, which is x squared plus 2x plus h squared. Or I'm sorry, 2xh. Let me erase that. So 2xh plus h squared. And then I'm going to subtract my f of x, which is x squared. And I'm going to divide by h. What you're going to find in this step is something always cancels. So it looks like I've got x squareds that cancel. So I'm going to have the limit as h approaches 0 of 2xh plus h squared over h. Okay. So in that first step, something's always going to cancel. If it doesn't, something's wrong. In this next step, what you're going to find is that in the top, you're going to be able to factor out an h. So we're going to say here, cancel something. In this next step, you're going to factor out an h. So I'm going to have the limit as h approaches 0. I'm going to factor out an h, which is going to leave me with 2x plus the other h over h. In this step, you're always going to cancel out an h. So I've got the h that I just factored out, and I've got an h in the top, or an h in the bottom, rather. So the h's are going to cancel. I'm going to be left with 2x plus h. And literally, this notation says let h become 0. Okay, this little h approaches 0 down here at the bottom says let h become 0. So what I'm going to do is say, okay, fine. I'm going to let h become 0. And when I let h become 0, I'm going to have the limit. Oh, I'm not going to have limit anymore because I'm going to go ahead and let that h become 0. And I'm going to go ahead and say 2x plus 0, and that equals 2x. So f prime of x equals 2x. And that's how we get the derivative when the function is not a straight line. So let's try another function. So this function, we're going to say g prime of x equals the limit as h approaches 0. The function is called g, so we'll say g of x plus h minus g of x over h. We're going to identify our g of x plus h and our g of x. G of x is going to be the easiest because it's just the function that was given to us, so x cubed. G of x plus h, I'm going to take the x out. So it was x cubed. I'd remove that x and put parentheses in. And in place of the parentheses, I'm going to put x plus h. X plus h to the third will expand using the binomial theorem. I'm going to attach a video of the binomial theorem in case you guys didn't cover it as much in pre-calculus. But the binomial theorem is going to expand so that we get x cubed plus 3x squared h plus 3xh cubed, squared, plus h cubed. Okay, so that's expanding using the binomial theorem. So we're going to have the limit as h approaches 0. I'm going to put in g of x plus h, so x cubed plus 3x squared h plus 3xh squared plus h cubed. I'm going to subtract g of x, which is x cubed, and divide by h. So in this step, we're always looking to cancel something. So if you look in the numerator, that's where you're going to cancel something. I've got an x cubed and an x cubed. One is positive and one is negative. So I'm going to be able to cancel those. That's going to give me the limit as h approaches 0 of 3x squared h plus 3xh squared plus h cubed over h. If you look at all those terms in the top, they all have an x, so we're going to factor out x. If I factor out an x, I get the limit as h approaches 0. I'm going to pull the h out and get 3x squared plus 3xh plus h squared over h. So then our move is going to be to cancel h, because we've got an h in the top and an h in the bottom. So we're going to have limit as h approaches 0 of 3x squared plus 3xh plus h squared. Now that we've done that, we're going to go ahead and let h equal 0. When we do that, we don't need the limit notation anymore because that's actually taking the limit. So we're going to have 3x squared plus 3x times 0 plus 0 squared. And that's going to leave us with 3x squared. So g prime of x is 3x squared. Okay. And let's try the next one, which I'm pretty sure is the last one. Nope, almost. All right, so this one, our function is called r of x. So we're going to be looking for r prime of x, which is going to be the limit as h approaches 0 of r of x plus h minus r of x over h. So for this one, to find r of x plus h, I'm going to look at my function, which is x squared minus 3x. I've got two places to plug in an x. So we've got something squared minus 3 times something. So I'm going to put in x plus h for both of those x's. If I expand this, I'm going to get x squared plus 2xh plus h squared minus 3x minus 3h. And then r of x is x squared minus 3x. So I'm going to set up the function. Limit as h approaches 0. We're going to start with r of x plus h, which is x squared plus 2xh plus h squared minus 3x minus 3h. I'm going to subtract my r of x, but because my r of x has two terms, I'm going to put parentheses around it. So I'm going to say minus x squared minus 3x. And that's all going to be divided by h. So we should have some stuff that cancels. If I look here, I've got an x squared minus an x squared. I've also got a minus 3x and what's going to be a plus 3x because it's minus a negative. So I'm going to go ahead and cancel those. So I'm going to have the limit as h approaches 0 of 2xh plus h squared minus 3h, and the rest of it canceled. So I'm going to divide that by h. Just like in all of our previous examples, I should have h factor out. So I'm going to have h times 2x plus h minus 3 divided by h. The h should cancel. So I'm going to have limit as h approaches 0 of 2x plus h minus 3. I'm going to let h go to 0. So I'm going to say 2x plus 0 minus 3, which is going to equal 2x minus 3. Okay, and all of these, notice h is changing, but x is staying constant. So that first point in the diagram that we had at the top of the page was staying constant, but it was the h value that was changing as we move the second point closer. So your answer should and probably will have an x in it. And so r prime of x is 2x minus 3. All right, let's try the last example, and then we'll talk about the alternate definition. So this one I left to last because it's a bit strange. So with this one, we're dealing with finding h prime of x, and we get the limit as h approaches 0 of h of x plus h minus h of x over h. Okay? So if I try and identify h of x plus h, that means I'm plugging x plus h into an x value. Problem is, there's no x value. Our function is just equals 4. So it's not 4x, it's not 4x squared, it's just 4. So at any x value, a constant is constant because it has the same y value. So even at x plus h, the y value is 4. So x plus h, h of x plus h, and h of x are both 4. Okay, no x value to plug into. So this becomes the limit as h approaches 0 of 4 minus 4 over h. Well, 4 minus 4 cancels out, just like we've had stuff cancel in previous examples. So that gives me 0. There are no h's to factor out, but 0 divided by 4, or I'm sorry, 0 divided by h, 0 divided by anything, is going to be 0. And the limit of 0 as h approaches 0, well, if I try and plug 0 in, like we've been doing, I don't have anywhere to plug it in. I'm just left with 0. So h prime of x equals 0. So this is a constant function. And when we take derivatives of constant functions, we're always going to get 0. Okay, so derivative of a constant is always 0. And that's because with our constant function, if I try and graph y equals 4, there it is, y equals 4 has a slope of 0 because it's a horizontal line. Its rise is 0, so there's no rise, there's all run. And so if the slope is 0, the derivative is 0. For this last piece right here, there's an alternate form for the definition of the derivative. And this is used when you're given a specific point. So the first set of examples that we did were left to be any point, to be determined later. But this is what happens when you have a specific point. So when I have a specific point, I'm going to pick a point C. Let me use my blue pen to just draw a generic function that we're going to call f of x. So the point C maps to the y value f of c. And I'm going to pick another point somewhere else, and it can be any point, so I'm just going to call it x. And that point maps to f of x. Well, I can connect those two dots with a straight line. I'm going to connect them with a green straight line. That secant line that we talked about before. If I write out the slope of that secant line using the points that I have, it's going to be f of x, so y2 minus y1, so the difference between my y values, divided by the difference between my x values. And ultimately what I want is I want this second point to move towards the first point. So I want x to get closer to c. I want x to become c. And so you see that here in the notation as x approaches c. So we're taking this right here, the slope of the secant line. Oops, let me make that yellow. So the slope of the secant line, and that's right here. Okay, and so that can be used when we have a specific point, and we'll deal with that as we go through the next couple of sections.